All right. Welcome to Intro to Rust. I hope my mic and everything is working. In theory, it should be. And I will be recording this session so people can watch it later. But all right, first things first, I'm Curtis. I have no professional background really, but I know a lot about Rust, so I'm running an intro to that. Table of contents. We're doing all this stuff. These are kind of the main parts of Rust that you need to know. And that's what I'm going to teach about. So first things first, what is Rust? Well, Rust is a systems programming language centered around speed and safety, right? You have languages like C, which is really fast, but it's also not safe. It's really easy to, reference unallocated memory and get a seg fault or something like that. On the other side of the spectrum, you have stuff like Java, which is really safe, but it's also pretty slow. So why is Rust? That's kind of part of the first thing. Rust exists because there's no other language really like it that combines both speed and safety. So Rust is there to have those two things. And the last thing is beware, not for the faint of heart. If this is your first time with a programming language, like you've never programmed anything before, you're going to have a hard time. I'm assuming you have prior experience for this workshop because Rust has a very steep learning curve. It's pretty difficult to do this as a very first language type deal. So I wouldn't recommend it, but it can be done if you're if you're really determined. Also, I am watching the chat for questions. So if you have a question, drop it in the chat and I will address it as soon as I can. All right, getting started. First thing we got to do is install Rust, of course. So we're going to use a cool tool called RustUp, which is short for Rust Updater. And basically the way RustUp works is you type RustUp update into your command line and it'll update and install Rust. But obviously first we have to install that. So we're going to click this link, which takes us to rustlang.org/tools/install. You can pretty much Google Rust language installer and you'll get this. But yeah, this is where you got to go. So using RustUp is the recommended way to do it. If you're on Mac OS or Linux, you can use curl to download it. Alternatively, on Linux, you can use apt if you have that. So for example, if I go to my terminal, you could do like sudo apt get RustUp. I already have it installed, so I'm not going to bother, but that is an option. And then for Windows, I don't think it's showing me because I'm on Linux, but through Windows, you can download like an installer executable. Oh, see other installation methods if you're on Windows. So if we go here, it'll take a bit of reading. It's not super intuitive, but you can just find a Windows installer that will install RustUp for you. And after you've done that, just run RustUp update and get the latest version of Rust, which is what I'm running on. And then to see if Rust is installed properly, you can do rustc, which is the Rust compiler, -- version. And it'll tell you what version you're running. And the next thing is cargo. So cargo should be installed with RustUp. And cargo is essentially the, if you know Node.js, like NPM, Node Package Manager, cargo is basically that for Rust. So we're going to do a version check on that to make sure it's working as well. And as you can see, I'm good to go on that. So now we're going to create a Hello World project. All right, to do that, we're going to use cargo. So you're going to want to go to a directory where you want your Rust projects, and I'm in a directory called Intro to Rust. If I list off everything in here, I just have my reference project. That's the only other thing. So to create a new project, you just say cargo new, and then your project name. I'm going to call this live because it's the live version of my Intro to Rust thing. I'll press enter, and boom, it's done. So now we're just going to go to the live directory. And if we list off everything in here, sorry, I'll do ls-a. There's not a lot. as you can see, but we will say code period and open VS Code in this directory. One little, I guess, extra thing, if you're using VS Code for Rust, I would recommend installing an extension, which is called, which one is it? Rust-Analyzer. This will give you auto completion and syntax highlighting for Rust, which is really, really handy. All right. So now, if we go to source here and main.rs, this is our main file. Like a lot of programming languages, we have a main function. And all it's doing here is saying print line, hello world. So you might be wondering what this exclamation mark is. This exclamation mark denotes a macro. So print line is actually a macro and not a function. The reason it's a macro in Rust is because Rust functions cannot have a variable number of arguments, but with print line formatting, which we'll see later, you can have as many arguments as you want, so they have to make it a macro. And it's actually very, very handy the way they've done it. And one other thing I'm going to do just for my own sanity is switch from spaces to tabs, because tabs are better than spaces, and that is the hill I will die on. All right, so as you can see, we already kind of have a Hello World project, so let's just run that. And the way you do that with Cargo is just by typing cargo run, and it'll compile and run. And as you can see, it prints Hello World, just as you'd expect. So now I just want to quickly go over formatting. Essentially, the way formatting works is like in a lot of other languages, you do your braces, and then anything that can be formatted, you can put in there. So I will put world. And if we run that, it prints the same thing. But now if I change this to like my name, it prints my name. And that's basically how formatting is going to work for everything. We will go over a little bit of extra stuff when we get to it. But for now, that's all you need to know for formatting. It's very, very simple and easy. All right. Let's go back to full screen here. Next thing, some common concepts. So the first thing we're going to be going over is variables. So variables, how do they work? Well, you say let, and then the name of the variable. So we'll say name, and you set it to a value. Now this little type thing here is from Rust-Analyzer, that extension I installed. There's not actually any words there. But now I've declared a variable called name, and I've set it to my name. And in a similar example, if we say hello, and then add in name, and we run this, we get, oh, hell, cool. Change that to hello. We get my name. So one thing I want to go over that's pretty important in Rust is mutability. So by default, all variables are immutable. This means they cannot be changed. So in most programming languages, you could say like name equals something and then print it. And we could say like name equals something else, for example, Joe, and then print it again. But as you can see, oh, not Joe, sorry, name. But as you can see, this has an error. Cannot assign twice to an immutable variable. This is because by default, name is immutable. Now, if we do try to run this using Cargo, we get essentially the same error with some really, really handy, essentially like pointers telling you exactly what you've done wrong. And this is how pretty much all error reporting works in Rust. It will tell you exactly what you've done wrong, which is really, really nice and handy. In some cases, it even says like what to do instead that'll fix the error, but that's not for everything. So what it's saying here is consider making this binding mutable. So if we make it mutable, and that's simply done by writing mut after let, right? Now we have a mutable variable called name. And if we run this, everything works perfectly fine as it should. All right, so another thing in Rust is all variables have a value. There's no such thing as null. So when you initialize a variable, you have to assign it. For example, if we say let age, and we just declare it, but don't assign it, we get an error. Type annotations needed because age doesn't have a type, which, okay, fair enough. And I'm going to go over type annotations later and how they work, but we will get to that. So if I do this, we get a new error saying, you know, we're borrowing a possibly uninitialized variable because age might not be initialized. In Rust, everything has to be initialized before it can be used. So the way, oh, you know what? I think I just realized I forgot to announce that I'm starting this event. Maybe that's why no one's here. Oh, someone else did it. All right, we're good. We're good. Sorry about that. All right. So if we declare age and we don't initialize it, it gets angry. We can initialize age on a different line, and this works fine because age wasn't assigned to. It had no value, and then it was assigned to. But we can't assign it to like null or something. Like we say age equals null. We can't do that. This doesn't exist. Null is not a thing. So null doesn't exist. But what if something won't necessarily have a value? Well, this is where option comes in. Option is a construct in Rust that allows, well, it's a tag union. If you don't know what that is, it's essentially an enum, but with a value for each variant. So it's a tag union that has some and then a value, or none and no value. So what we can do is we can say option equals none. And as you can see, it's an option of an unknown type, which is why there's actually an error because we need type annotations. If we say set it to sum 5, as you can see, now it's an option of type I32, and I32 is just a 32-bit integer. So you might be wondering now, okay, what's the difference between using an option and using something like null? Well, the difference comes in when you try to do stuff to an option. For example, in most programming languages, if you have a value that's null and you do something with it, you'll get like a null reference exception. Like if I want to say option dot whatever, in most programming languages, if it was null, you would get a runtime exception. In Rust, you have to unwrap this value before you can access it. So the way that works is we could say let value equal option dot unwrap. And basically what this will do is if option is set to some, like some value, it will return that value. And if option is set to none, it'll crash the program. Now, another thing that might be a bit smarter is to say, you know, if option dot is sum. So we're saying if this option has a value, we'll say value equals unwrap, and then we will print that. And if we print that, as you can see, it just says option is 5, which is what we'd expect. But then if we set option to none, and we will have to annotate the type here. If we run this, as you can see, it doesn't print anything because option doesn't have a value. So we can do an else case here and say option has no value. As you can see here, okay, option has no value. So this is the way you can have things that don't have a specified value. And the reason Rust elected to do this as opposed to just having null is because there is so much more you can do apart from this very basic example. Option is an extremely useful class that helps with a lot of things. Oh yeah, it didn't start on YouTube? That's weird. I am multicasting. Let me double check here. Yeah, I am multicasting. So it should work on YouTube. If it's not, I honestly don't know why. I will quickly let Jordan know. Hopefully he can fix it. All right, there we go. I let Jordan know. We'll see if he's able to fix it. Yes, that's what we have for option. All right, so the next thing we have is variable redeclaration. So variables are immutable, but something you can do is redeclare them. For example, here we have option and it's set to none. For example, we could say option equals sum5, but like before, that'll cause an error because option is immutable. What we can do though is say let option equal sum5. And we can print option again. And what I've done here is this special formatting, this colon and then question mark, means to debug format it. Basically, this means what you're telling Rust is like, this is used for debugging, so just print sort of the value as it looks in code. And the reason I have to do that is if I try to do this without debug formatting, it says it doesn't implement display, which is essentially regular formatting, so we can't do that. And it even says, you know, use the debug format or pretty printed debug format instead. So we'll do that. We'll use the debug format. And if we print this, well, if we run this, as you can see, option has no value, and then we have an option, which is a sum value of 5. But now what's the difference between redeclaring something and assigning to a mutable variable? Well, the difference is that this let option is not the same as this one. They are two totally different variables. Essentially what happens is when I redeclare option and say let option equal this, I'm deleting this one off of the stack. So it's erased from memory. And I'm creating a completely new one. So another thing I can do is, since these are two totally different variables, this doesn't even have to be the same type. I can say let option equal like option, like a string. It doesn't matter because these are two totally different variables. They are not related in any way other than name. Does that make sense, or is there any questions on that one? I'm just going to hope it makes sense. But once again, if there's any questions, just drop them in the chat. All right, we're finally moving on to data types here. So one of the things we've already seen in Rust is that Rust uses inference whenever possible. Data types are inferred, right? In most languages like Java or C, you would have to write like int x equals 5. In Rust, you just write let x equal 5, and Rust figures out on its own that you mean an integer. Right? I mean, if we look at this, we have name, and Rust figures out it's a string reference. That's what the and str means. Rust figures out on its own this is a string reference. In this case, since we set it to none, we had to supply a type by doing a colon and then writing out the type name. And the reason we had to supply type is because, well, let's get rid of this. I mean, what type of option is this? Can you figure that out by looking at it? No. So essentially, we have to tell Rust that this is an option containing an I32. And these angle brackets here with a type inside of them, this is exactly like generics in most languages. That's what they're called in Rust as well. A lot of enums and Rust classes use them because they're really, really useful. Yeah, I can totally increase the font size if I can figure out how. Is it Control Plus? It totally is. Is that better? I feel like that's a pretty chunky font size now. We should be good to go. All right, awesome. So in this case, where was I? Right, yeah. So in this case, since Rust can't determine just from none what this option is supposed to be, we have to specify it. And these are literally just generics like in every language. I won't be going very in-depth on generics because I only have like an hour to an hour and a half, and that would take a long time. We're already going pretty long already. But I will, at the end of this, I'll put other resources that will that are very good, and you can learn generics from there and stuff like that. Anyways, moving on. Let's type inference. Now I'm going to go over some numeric types. So by default, if we say some number equals an integer, it defaults to I32. Now, I32 stands for int 32, meaning a 32-bit integer, and specifically a 32-bit signed integer. Now, I'm assuming you know what signed and unsigned means. Actually, no, I won't assume that. Signed means you can have negative values. Unsigned means you can only have positive values. So in Rust, there are a few different integer sizes. There are 8, 16, 32, 64, and 128-bit integers. And we can specify those all with different types. And then unsigned and signed, I means unsigned. I means signed. And U means unsigned. For example, if we want an 8-bit unsigned integer, or a byte, for lack of a better word, that would be a U8 type. We can set it to some value. Another thing you can do is essentially postfix typing, like we'll say really big number equals 999,999,999. And then we can just put in the type of integer this is. So let's say I64. And then as you can see, Rust infers it to be a 64-bit int. So yeah, just use these to figure out all the integer types. You have 5 different sizes, and then either signed or unsigned, and that's all of them. It's a pretty simple system. Next, we have the Boolean and character types. So Boolean, it's exactly what you'd expect. We'll say let b equal false. And of course, there's also true. And we can print that out. All of these variables as well, you can usually print out. They usually come with default formats. But yeah, some Boolean is false. And as you can see, the type denotation for that is just bool. Next, we have character. Character kind of gets interesting. So we can set this. Well, this is a UTF-32 character. Or not a character. It's technically a scalar value, which is basically the same as character, but Unicode is really funky. The plugin I'm using to show variable types is Rust Analyzer. This one right here, it's available for VS Code, and it's really nice. And that's all I use. If you use Rust Analyzer, you can't use the regular Rust plugin because it causes conflicts and makes things kind of broken. So a character is a UTF-32 scalar value. What this means is you can essentially store any Unicode character in this, and Unicode is just a character encoding that supports every character from every language, literally ever, including emojis, which is terrifying. But yeah, you can put emojis in your strings and then print them. All right. So the next thing is, tuples and arrays. So these are fun. So Rust has really nice tuple support. So we can say tuple equals 4, 4, 4. What I've done essentially is I've created a tuple with the number 4, the character 4, and the string of the word 4. And if I print this, I think I need debug printing. So we'll do that. As you can see, it will just print out pretty much exactly what you'd expect. So the way you access something in a tuple is we can say let n4 for number 4 equal tuple.0. So this is kind of like array indexes. 0 is the first element, and then we would have element 1 and element 2. So let C4 equal tuple.1. Let S4 equal tuple.2. Now, tuples are enforced at compile time. Essentially, when you create this tuple, it is its own fully qualified type. So if I try to do something like doesn't exist equals tuple.3, as you can see, we get an error because there is no field 3 on this tuple, which, yeah, that's all that means. There is no field 3. Now, if I were to add it, field 3, as you can see, now it exists. So tuples are cool because they're fully qualified types, and they work very, very nicely. Another thing we can do is if we don't want to write something out like this, we can deconstruct a tuple by writing the names of each property. So N4, C4, S4, and then just set it to the tuple. And these values are going to be, respectively, 4, 4, and 4, if that makes sense. Like the number, the character, and then the string. And that's how you can essentially deconstruct a tuple very, very easily. Next is arrays. So arrays in Rust, much like in C or C++, actually, I don't know about C++, I don't remember, but in C, they have to be a fixed length at compile time. So we can let array equal 1, 2, 3, 4. Another thing we can do, this is a 4-element array of the numbers 1, 2, 3, and 4. And as you can see, it is typed as an int32 array with 4 elements. Another thing we can do is say other array equals 0, let's do U8 for fun, 4. So now what this does is this creates an array of zeros, and it creates 4 of them. And what this means, or let's make it 7, just for a different number. But essentially what this means is it's a U8 array. That's how we declare that there. And we're putting a default value of 0 into 7 spots in the array. This default value can be whatever we want. We could even set it to like 5. And then there would just be a bunch of 5s in this array. So now let's print these out. Actually, I think we can... It does need to be debug printed. now, if we run this, as you can see, we have an array of 1, 2, 3, 4, which is exactly what we declared here. And then we have an array of 5, 5, 5, 5, 5, 5, 5, which is also what we declared here, 5 and then 7s, or 7 5s, I should say. All right, so the next thing we have is the unit type. The unit type is essentially like the void type in C. For example, in C, you can say like void pointer equals something. In Rust, you can just say let nothing equal the unit type. So there is the unit type and the unit value. They both essentially mean nothing, right? So if something is of the unit type, it means it has no value. And if something is of the unit value, well, it's equal to nothing. So if we print this, I'm pretty sure we're just going to get the unit type. Yeah, as you can see, nothing just equals the unit type. And this is brackets because it's supposed to represent like an empty tuple. That's what that kind of means. But essentially, what this is used for is if you have a generic and you don't want it to have a type, you would put in the unit type. But other than that, you don't really use this. And the cool part about this type is it's literally size 0, like in memory. So this variable has no size. It is 0 bytes long, takes up no memory, and it's just referenced by a name. So it's pretty pointless outside of generics, but it does exist. And when we get to functions, a function that returns nothing implicitly returns the unit value. All right, and before we actually get on the functions, I do want to go over something actually, no, that's part of a different section, so I won't go over that. But now we're doing functions. Yay. The functions in Rust work pretty much the same as every other programming language, just with a different syntax. So to declare a function, you write fn, and then the function name, so we'll call this function hello. And then you have your brackets. So these brackets would contain any arguments you want. So we'll say name is a string reference. And I'll go over the difference between references and regular variables and all that stuff later on. But we'll say hello, name, and this will return the unit type. So this essentially means it returns nothing. And since the Rust developers are sane, you don't actually have to write this. It is implied. If you don't write anything for it to return, it implies that it returns nothing. Now in this function, we'll just say hello and then name. That's all we'll do. And then to call that function, we just type hello. And oops. And the name. Now if we run this at the very bottom, it says hello Curtis, which is essentially the same as what we had at the top, but we're calling it as a function now. So the next thing we'll do is we'll write a function that actually returns something. So we'll say add. So one thing I forgot to mention actually is your arguments to a function must have type annotations. And that's written by the name of the argument, a colon, and then its type. Right? Same thing we're doing here, name, colon, type. And then the return type is literally just the type it returns. Right now, it's throwing an error because implicitly we're returning the unit value, but it's expecting an integer. So it's angry at us. And all we're going to do is return a plus b. So this is pretty standard, right? So we'll print line 1 plus 2 equals add 1, 2. And if we run this, we get 1 plus 2 equals 3. But here is where things get a little interesting. So this part here where we're saying a plus b, that's known as an expression. It works pretty well the same as expressions in other languages, right? Like a plus b is an expression. We could add like divided by 5 or whatever. When you're manipulating values, it's known as an expression. So what we can do instead is just write a plus b with no semicolon. So the way Rust works, the last expression in a function is the return value. So this is a shorter way of writing return a plus b. We can just write a plus b, and it understands that this, being the last expression in the function, is the return value. And this might look weird at first, but it is very, very handy and makes for some really clean code when you get a little more complicated. But if we run this, as you can see, it works exactly the same as before. So that was expressions and implicit returns. So that's done. Next thing we're on to is control flow. So control flow works a lot like other languages, but there are a few key differences in Rust, mostly when it comes to syntax. So the first thing we'll go over is an if statement. If, I don't know, array 0, let's say array 3 equals other array 0. So an if statement in Rust, there's no brackets around the expression that you're checking. You can put brackets in, and that is valid syntax, but it'll give you a warning saying that the brackets aren't required. On the other hand, these curly braces are required. You have to have them. In some other languages, you can type if, and then if it's on the same line, you don't need any brackets. You always need brackets in Rust. Always, 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 you must have brackets. So if array 3 equals other array 0, we can say print line, the arrays are equal. And as you would expect, this is how array indexing works. Pretty straightforward. If you index outside the bounds of an array, the program will crash. So it's not like in C where if you access outside the bounds, you get invalid memory. It just crashes the program and says, hey, you accessed outside the valid bounds of this array. Now, another cool thing is the length of an array is declared at compile time, right? So if we access outside the bounds of an array with a constant value, in our editor, it doesn't say anything. But if we type cargo run, we get an error. We get a compile time error saying that this operation will panic. And panic is essentially Rust's way of crashing the program. And it says the length is 4, but the index is 5. And this is because we know the length of the array at compile time, and we know the index at compile time. So Rust can check at compile time if that array access is valid. But as we can see, the array index 2 does not equal the other array index 0, so this shouldn't run. So if we run this, as we can see, it doesn't run, which is perfect. And then an else clause works exactly as you'd expect. Holy moly, it's already been 40 minutes. Wait, no. Well, yeah, it totally has been. That's crazy. Anyway, the arrays are not equal. So if we run this, boom, bada bing, the arrays are not equal. Other control flow things include for loop, which is for, let's say, I in array. That's how that works. You say for some variable name in an iterator. So arrays are iterators. There are also other types of iterators. You can do whatever you want with I. So we won't print a line. We'll just print I. And then at the end of this, we'll print a new line. And if we run that, it should print 1, 2, 3, 4. If you want to iterate between two numbers, you say for I in, and then some range like 5 to 10. Print I, new line. And that will print the numbers 5 to 9. So 5, 6, 7, 8, 9. So that's how you iterate through a range of numbers. Next is, I believe, yes, the while loop. While loops work exactly as in every other language. While, so we can say let mute I, or we'll say counter equals 0, while counter is less than 10. Counter plus equals 1. Print. Counter. And then we will print a new line. So the main difference here is that, like if statements, you don't need brackets. Same with the for loops. You don't need brackets for any of these, but you do need the brackets for the actual body. If we run this, boom, we get the numbers 1 through 10. Lastly, there is a loop. So this is pretty interesting. It's kind of like a while loop, except there's no condition. It just runs forever. So if we want to do the same thing here with a infinite loop, we can say counter equals 0, and then loop. And then if counter is greater than or equal to 10, break. So break works like break in other languages. It'll just break out of the current loop. And this, yeah, will go until counter is greater than or equal to 10 and break out of the loop. If we run this, boom, we just get 1 through 10. And I actually forgot to print a new line, so I'll just do that. And there we go. Exactly the same as before. Now here's a really fun part about control flow in Rust. Every single one of these control flows count as expressions, which means you can assign them to variables, right? So we could say let x equal loop. Now keep in mind we have to put a semicolon here to make it a statement assigning to the variable x. And as you can see right now, x is the unit type because this returns the unit type. So in a loop, to return a value, you break and then return that value. So we could break counter. And then we could print line counter equals x. And now, as you can see, we run this, and we get that the counter equals 10 because we return the counter from this loop. If statements, to return a value from those, we can say if, well, we can say let y equal if x equals 10, and then else. Like a function, the last expression in an if statement is the return value. So if x equals 0, we're going to say y equals 10, else y equals 0. And that's all we're saying there. And once again, we need a semicolon. So if an if statement is being used as an expression, it must have an else statement, right? Because if you remember, every variable has to have a value. So basically, the if statement always has to return something. So you have if, and you can have else ifs in here, like we can say else if x equals 5. Right? We can return 5 if we want to. But we always have to have an else case. We always have to return a value from this if statement. And then for loops work like a loop where you can break a value. And same with while. In while, you can also break a value. All right. Next, this is essentially the core of Rust. This is what all of the Rust language is based around. And I've waited till now to explain it because, I mean, we need to know the syntax first before we can deal with ownership. So what is ownership? Well, ownership is essentially Rust's alternative to garbage collection or manual memory management. So basically, ownership means there's no garbage collection, which makes Rust really fast. But it also means you don't have to manage your memory manually. So you never have to worry about memory leaks. It just won't happen because you don't have to free memory by yourself. Rust figures all of that out at compile time and makes sure that everything is airtight. So the first concept is moving ownership. The first thing is when you declare a variable, right? We're going to make this a string. So string : from hello. When we create a variable, and this, by the way, is how you create a string. String and a string reference are different, and I'll get into that difference a little later. But we're going to create a string. And what happens is when a variable is declared, as soon as it's owning scope, so whatever scope owns that variable, once that scope exits, the variable disappears forever. So right now, this something variable will exist for the entirety of the program because the end of its scope is the end of the main function where the program closes. But if we create a function called take, and this is essentially going to take ownership of S, right? What happens is if we call take something, now you might think, like in most languages, after this function is done, you can use this something variable again, but that's wrong. This function becomes the owner of this string, right? So now this function owns this variable. And since this function owns S, when we get to the end of this function, S is freed at the end of this function. So here, if we try to print it, we're going to get an error because this value has been moved, right? So at this point in time, something doesn't exist anymore. It has been freed, right? This variable has been freed. It no longer exists. So we can't use it. And Rust ensures that at compile time, that you will never, ever, ever use a variable that has been freed. So we can't use this. But what if, right, hypothetically, what if we wanted to use a variable after using it in a function, right? Like we don't always want to give up ownership of our variables. Well, that's where borrowing comes in. So I'll write it like this to make it a little easier to understand. And here we'll say I am taken, or we'll say moved. I am borrowed. So if we, okay, so this is where borrowing comes in. Borrowing is essentially taking a reference to a variable. That's where the and symbol comes from. It's like taking a reference in C. And by referencing it instead of taking ownership, it doesn't get freed at the end of this function, right? Essentially, S, a reference to a string, is freed. The string is not. What happens here is if we say, if we redeclare something as a new string, and we pass it into borrow, what we're going to get if we do this normally is an error. Because as it says right here, it expected a string reference but found a string. So we just put a little and symbol here, and now we're passing in the reference. And then you'll notice we can still use this variable because we borrowed it instead of taking ownership of it. We have no errors. So if we run this, boom, bada bing. Hello gets moved and freed, but the borrowed hello gets borrowed, and then we can use it again because it was only borrowed. Now the next thing is mutable borrows. And we'll take an integer. So mutable reference to an I32. What does this mean? Well, we're declaring a function like normally, and then we're making it a reference, and we're adding this mutable keyword to say that we are taking a mutable reference to this variable, i.e. we can change the variable. So what we're saying here is the value at I, that's what the star means, we're going to set it to 5. Right? So that's the mutable reference to an integer. Actually, sorry, it's called I, not S. Is freed. The actual integer is not. What happens here is if we say let mutable x equal 5. Actually, we're going to do it this way first. Let x equal 5. And then we're going to say, actually, sorry, I set it to, yeah, okay. We'll say x equals 10. We're going to print x equals and then we're going to mutable borrow so if we try to do this, this syntax here is the same as taking a reference, like how we say and something, but we're specifying that we're taking a mutable reference. But we're getting an error. Why is that? Because x is not mutable. To give out a mutable reference to a variable, that variable has to already be mutable. So if we make x mutable, this is totally fine now. And if we run this, as you might expect, we have x equal to 10, because that's what we originally set it to. We pass it to this mutable borrow function, which changes it to 5. And then we print it again, and we get 5. Which is, like I said, exactly what we would expect. Now, there's a caveat to this. Part of Rust is memory and thread safety. And a part of this thread safety is you can only have one mutable borrow of a variable at any time ever. You can have any number of immutable borrows, right? So I could take a bazillion immutable references to x whenever I wanted to, right? Like if we say let ref x equal an immutable reference to x, this is totally fine. I can do this as many times as I want. But what I can't do is take a mutable reference to x more than once. If I take a mutable reference here, it's actually not angry because we don't use it at the same time. So we'll say mutable reference to x equals 900. If I do this, I get an error. And as it says right here, we can't borrow x as mutable more than once at a time. So this is because we're borrowing it here mutably, and then we're borrowing it mutably here again. So if we instead make this a regular reference, right, as you can see, we get an error here because we can't assign to a mutable reference, or an immutable reference, right? So excluding the star would have changed x to 5. For which part? Do you mean in this function here? So no, so if we exclude the star, I'm just going to comment this out so it doesn't get angry. If we exclude the star, we actually get an error. And the reason is because we're trying to assign a number to a reference, right? So the type of I is a mutable reference. Or sorry, the type of I is a mutable reference to an integer. So we can't actually set that to a number because a number and a reference are two different things, right? We could set it to a reference. Well, if we say let 5 equal 5, and then I equals a mutable reference to 5, now these are the same types, so we don't get a type error, but we do get another error. We can't assign to the immutable variable I, right? So, okay, we can declare the argument as mutable, right? But now we get another error. The variable 5 isn't mutable, so let's make this mutable too. Everything is mutable now, and it still doesn't work because 5 doesn't apparently live long enough. And what this means is that if we assign this reference, 5 gets freed before I does, because I is an argument. So it gets freed after the function is done being called. This would cause I to point to dereferenced or non-existent memory, which is not allowed. So we can't actually do that. Long story short, you can't just say I equals 5, because 5 is a number and I is a reference. Did that kind of make sense? Did that clear it up? I feel like that might have just been more confusing. Need to move on though. Hopefully that made sense. Back to this. So we can take any number of immutable references because it can't be changed. And as you can see, we can't assign to this because it's immutable. So we'll get rid of that. But we can take any number of immutable references, but only one mutable reference at a time, which means, okay, yeah, fair enough. Yeah, references are hard to wrap your head around at first, but the way I like to think about it is if you're passing something by a value, like for example here, where we're taking ownership of this variable, think of that like you are giving, like you as a person have the variable and you're giving the variable to your friend, right? Kind of the same thing. Whereas a reference is you're telling your friend, hey, if you want to use this variable, come talk to me and I'll let you use it. That's kind of the difference. Like one is you're giving it to someone else, whereas a reference is you're like telling them where to find it. All right, so yeah, that's mutable borrows. You can only have one mutable borrow at a time, so you have to be careful when you're handing them out. Now, there is another thing called cloning and copying. So some types are quote unquote copy types, and some types are clonable types. So a copy type is anything that's stored on the stack. And in Rust, the types that are stored on the stack are basically the simple types we went over here. So an option is stored on the, well, not necessarily an option, but integers are stored on the stack, Booleans are stored on the stack, characters on the stack, tuples are on the stack. The exception to this is if the tuple contains a heap type, then it's not stored on the stack because it has a reference to the heap. Arrays are stored on the stack. The unit type is stored on the stack, and etc. So these types are all copy types. And what that means is if we say function take copy, so let b equal true. If we take a copy of b, so what's happening here? As you can see in our function signature, we're taking ownership of this variable. Like it's not a reference, we're taking ownership. But here we can still use it afterwards. And I'll prove that by running the program. If we run it, as you can see, bool is true, and bool can still be used afterwards. Right, so what's happening here? Since Boolean is a copy type, just like many of these other types, like integers and characters and all that, instead of this function taking ownership, bool automatically copies itself into that function, and then the function takes ownership of the copy because bool is a copy type. That might be a bit confusing, but essentially it means for really simple types, you don't really have to worry about ownership because they just get copied around. Now, the opposite of this is cloning. If we say create another string, right? Normally, if we take s and try to print it after, normally this doesn't work because s has been moved, right? It complains about it. But what we can do, if we can't reference s, we can clone it. Right? Now, if we clone it, what happens is a lot like copy. We take a clone, right? We copy this string completely into a new variable and then give ownership of that to this function. And then we can still use s. And if I run this, right, I have moved a clone string, but it can still be used because we've cloned it. Now, generally, if you can take a reference instead of cloning a variable, you should take a reference because cloning is slow. So always use references over cloning if possible, but sometimes you do have to use clones. All right, and lastly, we have slices. So slices are essentially references to a part of an array. So what I mean is if we have an array like, for example, 1, 2, 3, 4, we could take a slice from index, let's say 1, 2, 3, which would give us a reference to the elements 2, 3, and 4. So we're essentially doing it without the first element. So this doesn't copy anything. It's literally just a reference to a certain part of an array. So, for example, we could say let array part equal array. And if you remember, this is the array we declared before. And we'll do the same thing, 1 to 3. So we're going to take indexes 1 to 3. Now, as you can see, this is angry because this means a slice of U8. So a type with square brackets around it means it's a slice. And it says we don't know the size of that compilation time, so we can't actually create a variable of it on the stack. That's okay because we can just reference it, and now everyone's happy. So now we have a reference inside of this array, and we can say array part is this reference. And if we run this, we get a part of the array, which is 2, 3. So I was actually wrong here. This goes from the first index to 1 before the last index, right? So yeah, that's how that works. So we're taking array. This slice means we're looking at array index 1 and 2. As you can see, it puts the slice right there. So this is really handy. You can also slice a whole array by essentially just referencing the array, right? And that takes a slice of, that takes a slice of the entire array. And well, actually, technically, it's a reference to an array. And if we want it specifically to be a slice, we can take a slice of the whole array and reference that. And then we do this, we run it, there we go. And this acts like a normal array. So we can print array part at index 1. and access it like a totally normal array, that works fine. And also, if we go out of bounds, it won't detect that at compile time. But as you can see, it panicked because the index was out of bounds. So we're not ever going to access invalid memory. But if we try to access out of bounds, it will crash our program. All right. I am running short on time. So I think I'm going to skip to error handling and wrap this up. So error handling in Rust works actually pretty, it's very cool. I like the way it works. So we're going to create a function, and we're going to say maybe could go wrong. And we're going to say, okay, fine. So what does this do? Well, we're declaring a function called maybe could go wrong, and we're returning a result. So this is Rust's built-in error type. If you remember option, we could return some value or have it set to nothing. Well, with a result, we can return okay, meaning everything was fine, or we could return error, meaning everything was not fine. And in this generic part here, this first type is the type of your okay return, and the second is the type of your error return. So the ways we can handle errors is a lot like using an option. We could say let result equal maybe could go wrong. And as you can see, this returns the result. Now, if we want the value, we can say unwrap. And like option, if the value is okay, it returns the value. If the value is an error, it crashes the program. Now, generally, you don't want to use this. You'll want to do something a little more clever and actually, handle the error without just crashing the entire program. But if you're like 99% sure or 100% sure that this will never error, you can just use unwrap to simplify things. But if we want to handle the error properly, there's more stuff we can do. For example, we can say if res.isOK, I can say value equals res.unwrap. Right, because now we know for sure that the result is okay. So we can unwrap it and say everything is okay and print the value. And we can say else error equal res.unwrap error. So this is essentially the opposite of unwrap. If the value is an error, it returns the error value. If the value is okay, it crashes the program. And that's all that means. We can do that. Now if we run this, since this returns okay, it should say everything is okay and then the number 5. But for example, if we change this to an error, and well, actually this has to be a string, so we'll say string from. If we return an error instead, what'll happen is it'll say everything is bad, something went wrong, which is pretty well what we expect. Now, this whole if statement is kind of verbose, right? Like it's big and it's clunky. What can we do to make this easier? Well, there's this thing in Rust called match. What you do is you can match against any enum value. So result is an enum, option is an enum, right? And you can match against these. And the way match works is you then put the possible results and what you should do when you get those results. It's a lot like a switch statement in other languages. So we can say if the result is okay, we're going to take the value That's what this V stands for. We're saying we want to take the value inside of the OK and call it V. Print line, everything is OK. And then print the value. And your next statement is followed by a comma. So you do comma and then the next thing. Error E. You print line, everything is wrong. And then print the error. So this does exactly the same thing as our if statement, but in way less lines, and it looks a lot cleaner too. So if we run this, everything is wrong, something went wrong, we get the same output, and then if we change it to OK again, we can run this, and we get everything is OK. So this does the same thing, just in a nicer way. The next thing we want to look at is panic. I'm kind of doing this in reverse order, but whatever. So panic is another macro, as you can tell by the exclamation mark. And essentially it means stop everything, something has gone horribly, horribly wrong, and shut down the program. And then you can pass a nice little message to say when you panic. So if we run this, what's going to happen is the program will run, and then it'll say thread main panicked at oh no. And then it gives you a nice little stack trace. So this is used for if either A, you reach a state that should be impossible, right? So if something should never, ever, ever be able to happen, you should panic about it and be like, hey, something's horribly, horribly wrong. You know, this should never happen. Another use case for panic is if you create a library. For example, I could create a library function that says this must be 5, and then I is going to be an integer. We can just say if I doesn't equal 5, panic. Right, so this isn't the greatest example, but it kind of gets the point across where if it's some input the programmer can control, you can just panic when that input is wrong or invalid, right? It's sort of like throwing an invalid argument exception in like Java or something, right? So we can say this must be 5, and if we pass in 5, everything will run normally. Everything is okay, 5. And it doesn't print anything because I didn't tell it to. But if we put in 7, it panics. I wasn't 5. And as a developer, I can go, oh, okay, so 7 is an invalid value, so I put in 5 because that's the only possible value. That's generally the only times you want to panic. If you've reached some sort of impossible or supposed to be unreachable state, or if something the programmer can control is invalid. And another thing I want to mention is that panic works exactly like print in that you can do all the fun formatting stuff that print can. So if we do this, it was actually whatever. We can say 9,000. If we run this, thread main panic, I wasn't 5, it was actually 9,000, right? So you can do all the fancy formatting stuff that you normally can with a print function. Yeah, that's generally when to panic. All right, so there's some other stuff that I didn't have time to go over, including, a part of this that I planned, but I didn't have time. Rust has first-class unit tests, which is really cool. Most languages you have to get a fancy library, do a bunch of crazy stuff. In Rust, it is first class and it just works. Another thing is generics, which I briefly mentioned but didn't really go over. Generics are a pretty big and complicated topic, but they're very, very powerful in Rust. Oh, so how do you catch an error like divide by 0? So in Rust, divide by 0 will cause the program to panic because divide by 0 doesn't have a defined result, right? So the program will panic and shut down, and it'll say, hey, you can't divide by 0. The way to actually catch an error like that is just to defensively program. That is the only way to do it. Another thing you can do, though, and actually I'll go to the Rust documentation for this. So if we go to I32 Rust, we go to the documentation here. You're going to go to the primitive type. And the Rust documentation is very extensive and very useful. So definitely check that out when you need it. But if we look at these functions, there is one called, for example, checked division. Checked integer division computes self divided by the right-hand side, returning none if the right-hand side equals 0 or the division results in overflow. So you can do this. And instead of panicking, Rust will return an option. So like it says here, it'll return none if the right-hand side is 0 or the division results in an overflow. So this is how you could catch a divide by 0 error without programming defensively. You could use this check division function and then check that option to see if it's none or if it has a value. That's one way you could do it. And they have these for a lot of things. A lot of stuff in Rust works like that. You can either program defensively, and if something goes wrong, your program will panic, or you can use these functions that return options and results in order to actually check if there's an error and then handle it gracefully if you want to. Anyways, back to this guy. Another thing I didn't go over is traits. Traits are a lot like interfaces in other languages. There are a few differences, but they're also very useful and very, very powerful. And I also didn't go over a lot of common collections, such as vector, which is a dynamic list, hash maps, none of that. I didn't have time to go over that. But luckily, all of this can be found in the Rust book, which can be found at this URL, doc.rust-lang.org/book. And I don't think you have to put in the title page, but if you just put in book, it'll take you there. This is mostly what I based the presentation off of. You can read this and you will learn pretty much everything you need to know about Rust. It's a really, really well done book. It's made by the developers of Rust. It's very easy to understand and very well explained. So if you want to know where to go from this workshop, go to this book. You will learn everything you need to know, more in depth from what I could cover in this limited amount of time. And you get to learn just more stuff in general. Like there's so much more info on ownership, and they actually cover structures and enums. They do more stuff on pattern matching. It's a really good book. I definitely recommend reading it if you want to learn more about Rust. But anyway, that concludes this presentation. Thank you so much for coming. I hope you enjoyed and found it informative. And happy coding.